factoring polynomials can be thought of as undoing the multiplication of polynomials, because what we're trying to do is rewrite a polynomial as a product of two or more polynomials. Now you may recall in this process you look first for a common monomial factor, and then after you look for a common monomial factor you look at the number of terms that you have to decide how to go about the factorization. Let's talk about the common monomial factor first of all. In these two terms we look at the numbers and the letters sort of separately and we decide what our common factor is. Well, in the 6 and the 4, 2 is a common factor. And between the x cubed and the x is a common factor. X is common to both terms, or both terms have as a common a common literal factor, one factor of x. So 2x is common to both terms. And we pull 2x out of this term, leaving 3x squared. We pull 2x out of this term, leaving minus 2. Now notice when the x comes out of that term, no x factors remain. No letters at all remain. We just have the minus 2. The one really nice thing about factoring is that you can always check to see if you have the answer correctly or if you have a correct factored form. And you check just by multiplying out the factors that you have listed. So is it the case then that 2x times this binomial will give us what we started with? And in examining that and seeing that we do have this, the product of these two will be that, then we do have a correct factored form. All right, here we have 3 terms involved. We're looking for a common factor. We can pull 4 out of all 3 of these terms. There's no letter that's common to all 3. These 2 terms have x's involved with them. This one doesn't. So there's no common letter factor. But 4 is a common numerical factor in all 3 terms. And so we could factor 4 out of them. We could also factor negative 4 out of them, and factoring a negative will serve the purpose of changing all of the signs in the polynomial that we start with. Let me show you what I'm talking about. When I pull negative 4 out of this term, I'm left with x squared. Negative 4 out of this term leaves negative 3x. And negative 4 out of this term leaves plus 4. So notice how the signs have changed. The first term here from minus to plus, plus to minus, minus to plus. A lot of times that technique of factoring a minus or a negative out of a polynomial is necessary to complete a certain form. All right, here we have a situation where the common factor turns out to be a binomial. Now the 2 terms here that are being factored are these 2 terms. And these 2 terms happen to have a common binomial factor. And those common factors, that binomial is treated just like a letter would be treated. If this were n times 2x and n times 3, we would know how to take out that common factor of n. Well, we take out the x minus 2 in exactly the same way. So we pull out x minus 2. From this term, we're left with 2x. X minus 2 out of this term leaves plus 3. So here's our factored form. One of the situations involved in factoring and using this idea of looking at the number of terms involved is a situation where we're faced with factoring the difference of squares. Now remember where the difference of 2 squares can come from. We had before that when multiplying the sum of 2 terms times the difference of 2 terms, we get the difference of 2 squares. So it kind of makes sense that when we're faced with factoring the difference of 2 squares, they're going to factor into the sum of terms times the difference of 2 terms. So if we have x squared minus 9, we factor into, let's see, the product of 2 binomials. One of them has a plus sign in it, the other minus. And we just ask ourselves, what is being squared to give each of the 2 terms? And we're identifying the items that are in the 2 binomials. X times x to give x squared, 3 times 3 to give 9, and the signs are different and we're all done. Now here's a situation where this is not the difference of squares, but we're supposed to look for a common factor when we begin the factoring process. And here we have 3 as a common factor. And when we take the 3 out of this term, we're left with 1. We take 3 out of this term and we're left with minus 4x squared. Now, once we take out that common factor of 3, we see that here we have the difference of squares. And a lot of times a common factor can mask a certain kind of special factorization process, because we'd be looking for the difference of squares. We don't see it here. We might think it's not available to us, but yet we can see it once we've taken out the common factor. That's the idea. All right, so now that we've taken that common factor out, let's see, we have what squared to give 1? Oh, 1. You see, and then we have plus and minus. And then what squared to give this? Well, think about the numbers and the letters sort of separately, and we find this to be 2x, 2x. Here's one where we also have the difference of squares. The numbers are getting a little bit bigger, and we have an exponent of 4 here on the x. No matter, it's the same idea. We go about the business of identifying the items in the two binomials. Now, what is being squared to give 16x to the fourth? Well, 4x squared, you see, is squared to give 16x to the fourth. So we have plus, minus. For 81, it's 9 times 9. Now, a lot of times there's a tendency to just stop the factoring process once we go through one step, sort of like this. But always check to see if one of the factors that are in an already factored form is factorable even farther. And here we see that. We have the difference of squares right here. Now, we can't factor the sum of two squares, but we can factor the difference of two squares. So we'll take this factor and simply bring it down, and then factor this into the sum of terms times the difference of terms. It's 2x times 2x to give 4x squared, and it's 3 times 3 to give 9. One's plus, one's minus, and we're all done. Here we have a situation where, and I've copied this wrong, this is x minus 2 squared minus y squared, and this is the difference of two squares. It's just that one of the terms being squared happens to be a binomial. But that's no big deal. You're just following through with the same kind of technique that we've been talking about. Pop in a bracket here, I would suggest, and use the same idea that we had before. What's being squared to give this first term? Well, this binomial is squared, you see, and so you list the binomial here in both places, and then it's the plus minus idea, and then y is being squared for this last term, and this is the factored form. We probably would drop the parenthesis within the brackets, and even the brackets can change into parenthesis like this. Oops. So we have x plus 2 plus y, x plus 2 minus y as the factored form. Now, I said that the difference of squares is factorable. The sum of squares is not factorable. There are other binomials that are factorable. The sum and difference of cubes are both factorable, it turns out. Now, the factorization, though, is accomplished by sort of a pattern recognition. And it turns out that for both the difference and sum of cubes, the pattern is binomial times trinomial. Now, let me just create a little space here. So, if we understand that the pattern is binomial times trinomial, we would start with the pattern. Just start with the skeleton of a binomial times a trinomial. And we identify the binomial part first, and then the trinomial part from the binomial part. Okay. For the binomial part, we just identify what's being cubed to give each of these. X is being cubed to give x cubed. 2 is cubed to give 8. And the sign that appears here is the same as this sign, so it's minus. To identify the parts of the trinomial, the first item in the trinomial is this first item in the binomial squared, so it's x squared. The last term is this last term squared. The middle term is the product without regard to sign. And it looks like to me I need a little more room here. Let me just stretch this out a little bit, make it look a little cleaner. Okay, the middle term is the product of these two without regard to sign. So 2 times x, 2x. And the sign turns out to be opposite that sign. If that's minus, this is plus. And if that's plus, this would be minus. Okay, let's go through it again. This time we have the sum of cubes, and once again we have the binomial times trinomial situation. So let's see, for the binomial part, what is cubed to give this? Oh, x. What's cubed to give that? 5. Sign is plus, so plus. First term here is that guy squared. The last term is this one squared. And the middle term is the product of these two without regard to sign. So we have 5 times x, 5x, and the sign is opposite this sign, so it's minus. So here's our factored form. Factoring a trinomial, you may recall that generally speaking, if it is factorable, then it's going to be a binomial times a binomial. And we're sort of using a trial and error method here to complete the factorization. So we think about binomial times binomial, and we remember the FOIL method, and we understand that it's probably the case that this first term, you see, of the trinomial to be factored, particularly if it's in standard form. The term of highest degree is here. So it's the first term here times the first term here to give the first term there. So it's x times x to give x squared. Then we look at the sign pattern. We see that the sign of the last term is positive. So that means that the signs of these two terms have to be the same, plus times plus or minus times minus, to give a positive result. We look at the middle term. Oh, it's negative. That means it's minus times minus. Now, factors of 12 are going to go into these two positions, but there are a lot of ways to factor 12. 12 could be 4 times 3, it could be 6 times 2, it could be 12 times 1. Now we understand that the minus 7x is the collection of this product and this product. So really we are looking for factors of 12 that add to give 7. That's the idea here. We can think all the way through the factorization of a trinomial like this, particularly when we have a leading coefficient of 1. We can easily think through the whole situation. So we have the 4-3 combination, factors of 12 that add to give 7. We can verify the factored form, x times x to give x squared, minus 4 times minus 3 to give 12, minus 4x minus 3x gives minus 7x, a correct factored form. Now, here's one with a leading coefficient that's different from 1. It presents us with more options, I guess, to try in this trial and error process. The factors for 2x squared would presumably be 2x times x. Now, the last sign is negative, so it's a plus-minus combination. And just guess at this. There's no real easy way to determine whether the plus goes here or there. So just take a shot and put something down. Now, factors of 15, probably the 5-3 combination. You might try the 5. We could try the 5 here and the 3 here. We would have 3x minus 10x. 3x minus 10x, that's negative 7x. Gee, that's not it. So that's not right. So the 5-3 combination might go the other way. Let's try 3 here. Whoops. Let's try 3 here. No, excuse me. Let's try 5 here. I had it right the first time. And 3 here. So we have 5x minus 6x. But minus 6x plus 5x is negative 1x, but we want plus 1x. What's wrong with this picture? Well, all we need to do is swap signs, make that a plus, make this a minus, and we should have the right factored form. Let's verify the middle term. Minus 5x plus 6x is plus 1x for the middle term. Correct factored form. Here's another one. This one happens to be a rather special one, but it doesn't look particularly special on the surface. Let's just go through and factor using our sort of trial and error method, x times x to give x squared. Last sign is plus, so these two signs are the same. Middle sign is negative, so it's minus minus. Factors of 25 are probably 5 and 5. Let's verify the middle term. Minus 5x with another minus 5x would give minus 10x. A correct factored form then is what we have here. We notice that we have a couple of binomials times one another. That is, we have the same binomial appearing as a factor twice, and we can indicate that as x minus 5 all squared. Now, this is called a perfect square trinomial because it comes to us as the square of a binomial. So we have a binomial squared giving us a square. So it's a perfect square trinomial. That's why it's called that. Now generally, we could go through and evaluate a lot of trinomials like this and try to identify those trinomials that are perfect square trinomials and go directly to this factored form. But it's really not worth the effort. Using the general method usually works out just as well. In order to identify a perfect square trinomial, understand, you'd have to recognize this is a square. That's easy. This is a square. That's pretty easy. The sign here has to be plus. And this middle term has to be fundamentally the double the product of the two items being squared to give those two. You see, that's the idea. We'd have to recognize all of that to recognize that as a perfect square trinomial. And again, it's not really worth the effort, unless you had about 50 of them to work. Another situation involving factoring is the notion of having four terms. Now remember, I mentioned early on that you kind of jump start your logic pattern of factorization by looking at the number of terms involved once you have tried to take out a common monomial factor. Well, the technique that's used when four terms are involved is the method of factoring by grouping. Now, factoring by grouping works like this. Now, we would look for a common factor, we don't see one. Then we would group. Put these two together, think of those two together. With these two, we have a common factor of x squared. When I snag out the x squared from this term, I'm left with an x. When I snag x squared out of this term, I'm left with minus 2. Now I shift my thinking over here. 3 is a common factor over here, so I could take out a 3. Now look at what happens if I take plus 3 out of these two terms. If I take 3 out of here, then I have minus x. If I take 3 out of here, then I have plus 2. Now look at these two. Oh, x minus 2 and minus x plus 2. Wow, what can I do to make those look alike so I can factor further? Well, if I can just get these two signs to change, then I'll have the same binomial in both of these terms. And I can accomplish that rather easily. All I needed to do was to, instead of taking out 3 from these two terms, just take negative 3 out of them. So negative 3 out of this term would leave x, and negative 3 out of this would leave minus 2. Now I have x minus 2 in both of these, so I can pull x minus 2 out of each of these terms. X minus 2 out of this term leaves x squared, and x minus 2 out of this term leaves minus 3. So our correct factored form. This, by the way, is not the difference of squares because 3 is not a square. In this one, once again, we have 4 terms. We would look for a common monomial factor. We don't see one, so we would go through the method of factoring by grouping. Now, by the way, you might be thinking, well, gee, why did we group the first 2 terms together? Why not group, for example, x cubed with minus 3x? Those have a common factor, and then these two together. Well, you know, it turns out that way of grouping would work. There's a third way of grouping. We could group x cubed and 6 together, and then these two together. Would that work? Well, it turns out that there are 3 grouping possibilities in problems like this, and 2 of them will work to give a correct factored form, and the third one will not. So, but to resolve the situation, if the polynomial is relatively normal looking, then just write the terms in standard form and group from left to right, and that generally will take care of almost all of the situations. Here, for example, notice we have this in standard form, and so I would just kind of group from left to right, this pair and then that pair, and that's probably the right way it's going to work. All right, for these two, I have, let's see, 5 is a common factor of both terms, and x squared is in both terms, so I'll pull 5x squared out of these two terms. 5x squared out of this term leaves x. 5x squared out of this term leaves minus 2. And for those two terms, I see that 3 is a common factor. When I pull 3 out of this term, I'm left with x. 3 out of this term leaves minus 2. And I have x minus 2 as the common factor in these two terms. When I pull out x minus 2 from this term, I get 5x squared. When I pull x minus 2 out of this, I get plus 3. So here is the correct factored form.